Welcome dear students. So this will be our last topic before this exam. We are going to start today slope stability analysis, and due to time limit we will do only very introductory kind of analysis. So our outline of the presentation will be like this. First we will see what are the various types of slope failure. You all understand what is a slope. So we'll see the types of slope failure, and then what is slope stability analysis, what is its objective, and what are the methods available. And then we'll discuss about the relative merits and demerits of these methods. Then we'll classify the slopes. We can classify slopes in a different manner depending on the context or purpose of classification. We will here classify the slopes into finite and infinite slopes for the purpose of analysis, and then we will cover a little bit of analysis of infinite slope. Although most of the real slopes are finite slopes, because of time limitation we will not be studying slope stability analysis of finite slopes because it's a very huge topic. I will cover a little bit of analysis of infinite slope. Alright, so first let us see what are the types of slope failure. There are different classification by different authors. One such classification scheme is this, which classifies the type of slope failure into fall, topple, slide, lateral spread, and flow kind of failure. Fall means the soil or rock mass detaches itself from the slope material and then falls under the action of gravity. Usually rock fall is common near hilly roads. Okay, so this is what is called fall. Then comes topple. In topple it is also like a fall, but what happens is in topple failure the mass overturns about an axis passing slightly below the CZ due to the downward force of gravity, and thereby it topples down. It just doesn't fall directly, it rotates and then falls down. Okay, so that is what is called topple failure. Then slide is the most common type of slope failure. You are all familiar with landslides, very prevalent here in this region, particularly during monsoon. And here the movement of the slope material takes place above a failure surface, and depending on the soil conditions, geometry, hydrological conditions, the rupture surface may have different shapes and sizes, and accordingly the slide will be different in every individual case. Details of the slide movement will be different because of the formation of the rupture surface is different in different slopes at different condition. Okay, this is the most common type of slope failure usually we see. So here the slope material is failing above a failure surface. We call it rupture surface or failure surface, and due to the gravity the material above the failure surface just moves outward and downward. Okay, next comes the lateral spread. Lateral spread is a motion where mainly the material translates, doesn't really rotate, it translates over certain flowing kind of layer. Usually that layer is water bearing silts or sands. When the strength is decreased of this layer due to the overburden, due to the gentle slope, the overburden material, the lying over this water bearing sand or silt moves. Okay, depending on the condition of this layer, lateral spread may be slow or very fast. Okay, then comes the flow slide, where the slope material, sometimes already failed slope material due to oversaturation, it may flow like a viscous liquid down the slope. Okay, so this is called flow slide. Flow slides are usually extremely fast, and that's why very dangerous also. Okay, so these are some glimpses of different types of slope failure. So next we go to slope stability analysis. What is the objective? Our objective of slope stability analysis is to find the factor of safety against sliding. Find factor of safety against sliding. We'll be dealing here only with slide type of slope failure, because this type of slope failure only has very well developed methods. So we'll discuss that only. So we want to find the factor of safety. That means how safe the slope is against sliding. And if I have a factor of safety greater than 1, that means the slope is safe, but for design purpose we want a factor of safety at least 1.5. okay, remember this factor of safety is a strength factor of safety. Strength factor of safety, and not a load factor of safety. You remember in bearing capacity analysis, how did we get the safe bearing capacity? Say QNS, net safe bearing capacity was QNU by factor of safety. So it is the ratio of ultimate load. The factor of safety is the ratio of ultimate load by service load. So this factor of safety is defined in terms of loads, whereas in slope stability analysis we define factor of safety in terms of the strength. Since you know that the soil fails in shear, therefore it is actually the ratio of shear strength by the shear stress acting. Okay, or it may be sometimes defined as driving force, resisting force, force or moment by also driving force or moment. Sometimes this factor of safety is also defined, although it is basically strength factor of safety, it can be expressed in terms of ratio of resisting force to driving force and so on. Okay, now there are different methods of slope stability analysis. The most commonly applied method is the limit equilibrium method. In limit equilibrium method, what we do, we assume a kind of failure mechanism. Assume failure mechanism. Okay, and then we find the factor of safety for that failure mechanism, and I need to find out the minimum factor of safety by assuming different failure mechanisms. For example, suppose I want to do a slope stability analysis, then what I may do is this is one possible rupture surface, I may take another possible rupture surface, okay, maybe in some case maybe this rupture surface will give me a lower factor of safety, okay, only the top of the slope may fail, or sometimes the base failure, this is a base failure sometimes, or I may also have a failure surface somewhat like this, okay. Usually we assume it to be a circular one, okay, for ease of analysis, but we may have different planar failed surfaces also, okay. There is one method, Newmark's wedge failure method, where we assume that the failure surface can be made up of different planes, somewhat like this, okay. So our job is to find out that mechanism which gives me the minimum factor of safety. So it's a trial and error procedure, many repeated analysis, similar analysis must be repeated for finding the actual factor of safety, okay. That is the disadvantage of this method, okay. But the advantage is that it can be easily done once you know the method, once you can determine the driving forces and resisting forces acting on the potential failure surface, then you can easily do the analysis, okay. And there are many methods under this category of limit equilibrium method. We will not study all of them right now. The limitation is that your factor of safety depends on the assumed failure mechanism. So factor of safety depends on the assumed failure mechanism. That is the biggest disadvantage. So we must be able to correctly figure out what is the failure mechanism, possible failure mechanism, to get the correct factor of safety, and it needs little bit of quite a bit of experience, in fact, to do a good slope stability analysis by this method. Then there is finite element method. You are already familiar with the method. You must have been studying taking finite element course also, C5203. So in finite element method, the advantage is that we don't need to assume any failure mechanism. No assumed failure mechanism. So we don't need to pre-assume a certain failure mechanism. The soil is allowed to fail, the slope is allowed to fail in its own natural way in the modeling, okay. And therefore I can also simulate the progressive failure over time of a slope failure, okay. And sophisticated analysis FEM methods are available where I can take into account the hydrological conditions in addition to the geotechnical conditions. Hydrological conditions. Can be incorporated. Okay. But the limitation is the whole success depends on the accuracy of model, your FEM model. FE model, how good your modeling is and how good your constitutive relations are. Okay, so you need sophisticated soil constitutive relations, that means soil stress strain relation, that how the stress develops with strain over time in a nonlinear analysis. So you need good constitutive models. And another limitation is it takes a lot of time to prepare a model and to analyze it. Okay, so it takes time consuming, it is time consuming in short. Because preparing the model takes time and also the solution takes quite a bit of time. Okay, even with today's fast computers, in a very large problem we may need to go for parallel computation. Then we have types of slopes. I can classify slopes as natural or man-made. That is one of the most preliminary kind of classification, natural or man-made. Man-made slope may be the dams, embankments, etc. Okay, road cuttings, etc. Then we can also classify the slopes into finite and infinite slope. Infinite slope means what? Basically, infinite slope means it's a slope of large extent so that the end condition, that means the boundary condition at very far away in the soil model, slope model, does not affect your results. Usually what we have is, usually in infinite slope, suppose this is my slope, it's a very long slope, and usually what we can assume is that since the boundary doesn't affect the results, therefore at identical depth from the slope surface the soil properties are similar. Okay, and therefore if this is my slope surface, then the failure surface will be parallel to the slope surface in infinite slope. So that makes the analysis much more easier than in case of a finite slope, where I may have different kinds of failure surfaces that we have already discussed here. I have already shown different failure surface needs to be investigated in a finite slope, but in infinite slope it is not so, because the soil characteristics at identical depths from the surface are identical, because it is so large extent. Therefore my failure surface I can assume parallel to the slope surface. Okay, and that's how we define an infinite slope. All right, so let us go to analyze an infinite slope. First case, we are considering a dry slope, okay, without any pore water pressure, and we are assuming that the slope angle is beta with horizontal. All right, so this angle is beta, this angle is beta, and let us consider a slope material above the failure surface, and the failure surface is say at a depth of h vertically from the slope surface, and it has a width horizontally of length L. Okay, width is L and height is h, and therefore the area of this portion will be same as the area of a rectangle having height of h and width of L. Therefore I can now find out what is the W of the soil mass considered. W will be gamma into L into h, right, into 1 in the perpendicular direction of the board. Okay, that one we are not writing. So gamma into LH is my W. The soil has a unit weight of gamma, a cohesion of C dust, and angle of shearing resistance as phi dust. Okay, now when this weight W acts vertically, it can be resolved into two components. One is perpendicular to the plane of failure, and the other is the along the plane of failure. And when I do that, I denote the normal force, normal component of the weight as say N, and this N we can easily see that N is how much? W cos beta, right? W cos beta, because this angle is beta. Since this angle is beta, angle between two lines are equal to angle between their perpendiculars, so this angle will be beta. Therefore this N is W cos beta. And similarly the force tangentially acting, which is the driving force, this is the disturbing force that is causing instability of the slope. So this T is obviously W sine beta, right? W sine beta. Now this is my disturbing force, and what is resisting that disturbing force? It is the shear strength available along this failure surface. Okay, and that shear strength available based on Mohr-Coulomb failure law, the shear strength I can write it as say C dest plus sigma dest tan phi dest. Is not it? Now if this shear strength is the peak shear strength of the soil, then I would have written tau F equal to say Cf sigma f. Okay, but what may happen due to the deformations, you know that to mobilize the peak strength of a soil, you have done triaxial test, you know that the soil must undergo enough strain, that means a lot of deformations are needed, and that condition may not always prevail in the slope. Okay, therefore depending on the amount of straining, the full strength may not be mobilized, full strength may not be available at the failure plane, rather some partial amount of strength, which I am calling as tau m, mobilized strength, may be available. I am denoting it by C dash m plus sigma dash into tan phi dash m. Okay, sigma will remain same, only the angle of shearing resistance and cohesion will be different if it is not at its peak strength. Okay, so therefore I am calling it tau m equal to this. Now in order to find the value of sigma, what I need to do, I need to divide this normal stress by this area, right? Divide this normal force by this area. So therefore what is my sigma dash? Sigma dash is n divided by the inclined length, which I am denoting it as Li. Li, and you know that Li from geometry, it is L by cos beta, because L is Li cos beta. Okay, from this geometry, if you assume a triangle here, this is my L, this is my Li, so Li is L by cos beta. So if I now put the value of n here, W cos beta divided by L by cos beta, so W cos beta divided by L by cos beta, that cos beta will go up, so it will be W cos square beta by L. Is that right? Now we can put the value of W here from this equation, gamma L into H, so therefore sigma dash will be my gamma L H cos square beta by L, and this will give me gamma H cos square beta. I'm sorry. So gamma H cos square beta. Okay, so I get this equation. Sigma dash is gamma H cos square beta. Let me note down this equation. I'm very sorry. Okay, and similarly, what will be my shear stress acting? Shear stress acting will be shear stress shear stress. Remember, it is not shear strength, it is shear stress, so it is based on the driving force. Driving force is my T. Okay, and so again T divided by that inclined length, so L by cos beta, so T cos beta by L, is not it? And now I put the value of T is W sine beta, so it is W sine beta cos beta by L, and when I put W equal to gamma LH, then again I have finally gamma H sine beta cos beta. This is my shear stress. Okay, so let me note down this once again. So tau is equal to gamma H sine beta cos beta. Okay, let me again note this equation. This will be useful. Now I can define the factor of safety as the available shear strength by the mobilized shear strength. Okay, so now let us define my factor of safety as, now factor of safety, I'm sorry, these are all rectangles. Now my factor of safety is defined as Fs, which is equal to the failure shear stress, that means shear strength, by the mobilized shear strength. Okay, and this I can write as CF, I think I used CF, the notation. Yes, CF dash plus sigma dash tan phi dash F divided by Cm, C dash time mobilized value plus sigma dash tan phi dash m. Okay, now you see it has two parts, one is the cohesion part, other is the frictional part. Okay, and therefore we can also define as a factor of safety for cohesion Fc as, let me define it as C dash F by Cm, C dash m, and I can have another factor of safety for cohesion, for friction, which is tan phi dash F by tan phi dash m, this mobilized friction. Okay, the maximum peak shear strength by mobilized shear strength, and here the peak cohesion by mobilized cohesion, that gives me the factor of safety against cohesion. Now usually what I can take as, when my factor of safety, both factor of safeties are same, then what I can call, I can use a common factor of safety, and that is when Fc is equal to F phi, and that I call as Fs, factor of safety, general factor of safety, then Fs will be equal to F phi, so Fc, so C dash F by C dash M, and that will also be equal to tan phi dash F by tan phi dash M. Okay, we take this as the general factor of safety when both components of the factor of safeties based on both cohesion component and frictional component are the same. Okay, so this is another important equation. Now when this factor of safety is 1, let me add one more page. Now continued. When this factor of safety is 1, the slope is at the verge of failure, right? Because the shear stress and mobilized shear strength will be the same one. Okay, so at the verge of failure, I am very sorry, at the verge of failure, or at the limit equilibrium, or at the impending failure, what happens is Fs is 1, and therefore my actual shear stress acting shear stress will be same as mobilized shear strength, right? That's how the slope will fail. Mobilized shear strength. Okay, and therefore I will have tau will be same as tau m. Okay, now what was the value of tau? You remember, tau was gamma h sin beta cos beta, and what is my tau dash m? Tau dash m is c dash m plus sigma dash tan phi m dash. Okay, so I'll equate them now. So therefore I'll be able to write, let me write from here, gamma h sin beta cos beta will be equal to what? Tau m. Tau m is c dash m plus sigma dash into tan phi dash m. Okay. Now let us write down the value of sigma dash here. So I'll get gamma h sine beta cos beta is equal to c dash m plus, what was my sigma? Sigma was w cos square beta, I think. Yes, w gamma h cos square beta. So gamma h cos square beta into tan phi dash m, and therefore what I can do is I can take these two terms common. Then what I'll get gamma h times sine beta cos beta minus cos square beta tan phi dash m will be equal to c dash m by gamma h. Okay. Now I can multiply this term by a cosine term and then again divide it, so that I can take cos square beta common. In that case I will get this gamma h I have already written here, this is wrong. This will be only cm. Okay, this will be c dash m, and therefore I will have c dash m by gamma h will be how much? Will be this value, and this value I will write as, I'll take cos square beta common, then I will get sine beta by cos beta, so tan beta minus tan phi m. Alright. Now what I had, based on my definition of factor of safety, my FC was c dash f by c dash m. So c dash m will be c dash f by fc, and also I had f phi was tan phi by tan phi m. Now onwards I can even drop this f, okay, because we understand now that this is strength. We are talking about strength, not about the stresses. Okay, so I am dropping this f term, and when these are equal I have normal factor of safety Fs. So in terms of Fs I can write C dash m as C by Fs and tan phi dash m is tan phi by f, tan phi dash by fs. Now I'll put these values here in this equation. Okay, then what I will get, I'll write C dash m as C by fc, so I'll get C dash by fc into gamma h, sorry, not fc, it will be fs, because both are equal now. I'm considering them to be equal, so this will be equal to cos square beta into tan beta minus tan phi dash by fs. Okay, so now I'll bring the terms containing fs to the left hand side, and then I will get, after simplification, I will get 1 upon fs into C dash by gamma h plus cos square beta tan phi dash, cos square beta tan phi dash, this term cos square beta into tan phi dash, fs I have already taken out, is equal to cos square beta tan beta. Okay, and therefore what will be my fs? From this equation I can find fs. Fs will be this thing divided by this thing, and if I simplify this, I'll get just a minute. After simplification, you can find it easily. Fs will be equal to 1 upon fs is this, so fs is this whole thing divided by cos square beta tan beta. Okay, and this cos square beta tan beta can also be written as tan beta is sin beta by cos beta, so it is actually sin beta cos beta. I can also write it like this, right? Sin beta cos beta. Then my fs will be, in that case, C by gamma h sin beta cos beta plus this term divided by this term, so it will be it will be how much? It will be tan phi dashed into cos square beta by sin beta cos beta. So it will be cos by sin, so this is inverse of tan beta, so this is tan phi by tan beta, right? Let me write it down, the full this thing. I will have cos beta by sin beta. Okay, and this will give me cos beta by sin beta is if I bring it down, it will be tan beta. Okay, so therefore I'll get, hence factor of safety for this infinite slope will be, if it is C phi soil, it will be C by gamma h sin beta cos beta, or cos square beta tan beta, whatever way you like. Cos square beta into tan beta. Let me write it in this manner, because there is a tan beta term here, I can again take it common. So tan phi by tan beta and this I can write as, so Fs will be equal to C by gamma h C by gamma h into tan beta I can take common okay, so no further simplification is necessary. In fact, I can keep factor of safety like this. Okay, so this is my value of factor of safety. I do not know what has happened. This is my expression for factor of safety. Okay, so this is how I can get the factor of safety of an infinite slope made up of C phi soil. If it is only cohesionless soil, then this term simply will not be there, because C is 0, and in that case factor of safety will be just equal to tan phi by tan beta. Okay, so when factor of safety is 1, then tan beta becomes equal to tan phi in that case, and that means the dry infinite slope will be stable as long as beta is less than phi. Okay, so we can write it down here if you like. So for cohesionless soil, for cohesionless soil, I'm sorry, cohesionless soil, Fs will be simply equal to tan phi by tan beta, and therefore phi beta must be less than phi for a safe slope. Factor of safety to be higher than phi must be greater than tan beta, so therefore beta must be less than phi for safe slope. Okay, so this is another important result we have got when the slope is dry. Okay, next, in a C5 soil, I may find out at what depth actually the failure will occur. Okay, that means at what depth, what is the value of H here, which will make my Fs1, and that depth I will call H critical, or critical height of the slope in a C5 soil. Okay, so let us find out then the critical height of slope in a C5 soil. So critical height in C5 soil. So I will use the value of factor of safety as 1. So here, when the slope is critical, when I want to get that critical height, then I take Fs to be 1 and H to be the critical height, H critical say. Okay, in that case, from the expression of this factor of safety, what I can get? I can get this thing equal to 1, and therefore I will get gamma H critical into this thing is, I can write sine beta cos beta. Okay, okay, let me write down first cos square beta tan beta, doesn't matter, cos square beta tan beta. See, this is 1, so this C divided by this, C divided by this, plus tan phi dashed by tan beta is 1. Okay, and then if I simplify, I'll have here sine beta cos beta. So what I can do is, let me add these two fractions. Okay, so if I write tan beta equal to sine beta by cos beta, I will get sine beta cos beta here. Or let me put it gamma HCR cos square beta tan beta, and this will be C plus this will be gamma H critical into cos square beta into tan phi. This is my 1, right? And therefore I'll have this equal to this, right? So H critical, so from here I can get, let me write it here. Now I'll write it as sine beta cos beta. So gamma H critical sine beta cos beta is equal to C plus gamma H critical cos square beta tan phi. Okay, and therefore from here what I get, I can take this term this side, then I will be able to take gamma into H critical, I'll take common, then I will have sine beta cos beta minus cos square beta tan phi. This will be equal to C, right? And therefore I can write H critical. Okay, I can again this I can take cos square beta again common, then I will get gamma H critical. Actually I am doing the same thing again and again, that need not be done, into cos square beta this term will be sine beta by cos beta, so it will be tan beta minus tan phi will be equal to C, and hence I'll get H critical will be equal to C by gamma, C divided by this whole thing that I will just write in a simplified manner, into 1 upon cos square beta into 1 upon tan beta by tan phi. Tan beta minus tan phi. Now once again you can see here, as long as tan beta is as long as beta is less than phi, then only I have certain value of H critical. When tan beta and tan phi becomes 1, then this thing becomes 0, so I cannot determine any critical height. Okay, clear? And now if I divide, say, C by gamma H critical, will be what? It will be cos square beta into tan beta minus tan phi. And you can see that C by gamma H critical is a dimensionless number, because this is C is in kilopascal, gamma into H will be also in kilopascal, so it will be a dimensionless number. Okay, and that number also sometimes is very much useful, particularly for finite slopes. There is something called Taylor stability number. That idea comes from this formulation. Okay, now when phi is equal to 0 condition prevails, if the soil is purely cohesive, there is no and it is undrained, then what will happen? This term will not be there. Okay, and therefore I will get, for phi equal to 0 condition, phi equal to 0 condition, my C will become undrained C, that is Cu. In that case, H critical will be what? H critical will be Cu by gamma, undrained cohesion by gamma, times cos square beta into tan beta, 1 upon cos square beta into tan beta, and this is nothing but sin beta cos beta. Okay, so this is equal to HCR is Cu by gamma into 1 upon sin beta cos beta. Okay, so these two relations we got for critical height of the slope in case of C phi soil and in case of phi equal to 0 soil, pure clays. So these are also important relations. All right. Okay, let us go to the infinite slope, where seepage is occurring parallel to the surface. Okay, so there is a groundwater table at some depth. The height of the groundwater table from the base of the slope is, say, small h, and I am considering the total height from the failure surface as capital H, and the soil above the groundwater table has soil properties gamma, C dust and phi dust, and below the groundwater table we have gamma saturated, C dust and phi dust. Okay, now let us find out the factor of safety for this case. Now just like the earlier case, we will define the factor of safety as the shear strength divided by the shear stress. Okay, so what is my normal stress? We already got, the normal stress was sigma was equal to, the general expression was gamma h into cos square beta. Okay, this angle I didn't show it here, obviously it is beta. Alright, let me show it. I'm very sorry. See, this angle here is this angle is beta. So sigma is gamma h cos square beta, and what will be my pore water pressure at the failure surface? It will be gamma w into h okay into cos square beta in the normal direction. Cos square beta in the normal direction, and therefore my effective stress on the failure plane will be sigma minus u, and that will be gamma into h minus gamma w into h into cos square beta, right? Now also we have earlier found the shear stress, that means the driving force, driving tangential force divided by the area, was my gamma into h sin beta cos beta, or cos square beta tan beta, sin beta cos beta. These we already got, and therefore what will be my factor of safety? My factor of safety will be Fs will be equal to, let me draw a large line. I will have C dashed plus, I will put the value of sigma dashed. Sigma dashed is gamma h minus gamma w into small h into cos square beta cos square beta tan phi dashed. And then I have shear stress here, gamma h sin beta cos beta. Now obviously because of this term my sigma dash has decreased than in the dry case, so factor of safety will be decreased. Okay, now when the groundwater table is just at the surface, what will happen? When the small h and capital H becomes equal, in that case the whole soil is saturated, right? And therefore what I did, the equation will be slightly more simplified. Now for full submergence, for complete submergence, my H becomes equal to H and gamma becomes equal to gamma saturated, and therefore my factor of safety will be so this factor of safety becomes then this term remains same, C dash plus this becomes gamma submerged because H is H, so gamma saturated minus gamma W is my gamma submerged into H into cos square beta tan phi, and this becomes gamma saturated H sin beta cos beta or cos square beta tan beta. Okay, cos square beta tan beta. And this becomes equal to, we can divide it into two parts. One is for cohesion, the other is for friction. So C dash by gamma saturated into H into cos square beta tan beta plus we have gamma submerged by gamma saturated into what I get, tan phi by tan beta. Actually tan phi dash, I'm sorry, this should be tan phi dash. So what we have seen is that when the slope is completely submerged, this gamma saturated is greater than gamma, therefore the factor of safety, this term decreases, and also this, due to this factor gamma submerged by gamma saturated, this term also decreases, so there is an overall decrease in factor of safety of the slope. Alright, and for usual sands, you know that this quantity is nearly 0.5. So if it is a cohesionless soil, then this term will not be there, and for dry case my factor of safety was tan phi by phi dash by tan beta. Now it has become the earlier factor of safety, dry factor of safety, multiplied by this ratio gamma submerged to gamma saturated, which is about half. So for cohesionless soil, what happens for cohesionless soil. I'm sorry. Cohesionless soils, Fs in submerged, Fs for full submergence, becomes nearly half of Fs for dry soil. Okay, so this is another conclusion we have made. What happens in case of full submergence? Okay, so this is our conclusion, and the value of Fs becomes this. So this is how we can have different, we can see the change of factor of safety due to submergence in this infinite slope. Okay, so with this we come to the end of this lecture. Hope all of you could appreciate what we have discussed. So basically we have seen what are the types of soil slope failure, and what are the objective of slope stability analysis, the various methods, namely limit equilibrium method and finite element method. We have seen their advantages and disadvantages, and we have classified the slopes into finite slope and infinite slopes, and we have analyzed dry and submerged infinite slopes in C5 soil, got the values of factor of safety, and for phi equal to 0 condition and cohesionless soil, how the factor of safety modifies, that also we have seen. And we have also seen in case of C5 soil how critical height can be obtained, and in case of phi equal to 0 condition, how critical height of the slope before failure can be obtained. And we have seen the effect of seepage also. Okay, so wish you all the best for the exam. Thank you for attending the class.